So let's look at doing Fisher's discriminant analysis with the iris dataset. So we're going to use all three species, Setosa, Virginica, and versicolor, and all four covariates, so sepal length, sepal width, petal length, petal width. And we'll do the analysis ourselves first. So we'll first form the between covariance group. So if you load this package VCVComp, you can do this very easily with this cov.b command, and that'll give me the between group covariance matrix. Then the within group covariance matrix is cov.w. We've seen that already. That'll give us this. And then I'm going to form the inverse of W times the matrix B. Now, this isn't the most numerically stable way of doing this, and it's not how the R code does it, okay, but it's how we write it down theoretically. So let's just try it this way. So if we do eigenlist to find the eigenvalues and the eigenvectors, when we look at the eigenvalues, we can see that we've got two non-zero eigenvalues and two zeros, essentially. There's numerical error, as always, they're not quite zero, but they're essentially zero. And we expect that, right? We said that the rank of W inverse B can be no bigger than the number of groups minus 1. Now, there's three groups here, three species. Minus 1 gives 2. So we expect the matrix to be at most rank 2. And that's what we see. We've got two positive eigenvalues, and the matrix is rank 2. Okay. So let's now do the projections of the data onto the eigenvectors. So I've stored the eigenvectors here as the matrix B, and then in my new coordinate Z, I've just said let's do X transpose times V. But X here is they're already on the rows, so it's just the matrix X times B. And then I'm just plotting them, plotting coordinate 1 against coordinate 2, and I've coloured them by the species. And we get this plot here. And look how well it's done, okay? So the first coordinate is on the x-axis here, and you can see that it almost perfectly separates out the three populations. If I drew a vertical line here and a vertical line here, we would have close to perfect prediction accuracy. We saw that earlier, right, in the linear discriminant analysis. We had 98% prediction accuracy. It'd be very similar here for Fisher's discriminant analysis. We can see that the second coordinate isn't doing much. You know, the second coordinate doesn't separate the classes at all much. It helps separate versicolor and virginica a little bit, okay, but there's a big overlap between them still. So there's not a lot to learn by doing looking at this second coordinate. But we can see that from the eigenvalues. So if we do something we did similar to PCA before, and look at the eigenvalues over the sum of the eigenvalues, that tells us something about the proportion of something that they're explaining. So we can see that the first eigenvalue accounts for 99% of the sum of the eigenvalues, the second one less than 1%. And this is what R reports when we do LDA. So if we do LDA of species to a little dot, so for the iris data set, so doing exactly what we've just done here, we get reported this proportion of trace, and that's what it's done. Yep, it's given us the eigenvalues over the sum of the eigenvalues. These coefficients here are essentially the eigenvectors bound. Okay. There's some differences to what we did, and it's because of how they're implementing things. There's many different kind of variations you can do here, so it's slightly different if you look at them. Okay, but they're essentially the same to within one or two decimal, within two decimal places. Now we don't need to do this ourselves. We don't need to form the matrix W inverse B, find the eigenvectors, and so on. We can just use the built-in R command to do this, and there's also a built-in plotting command, although they're not quite as pretty, I don't think. Okay, so if we do plot of this LDA object, and again I've coloured the points by their species label, we get the same plot as above. Okay. It looks slightly different. because the y-axis is flipped here. But if I was to multiply the y-axis here by -1, we get the same plot. Okay. And it's also put the class labels in as well. Now, if we do this plot command with a dimension equals 1, and remember it's only the first LDA coordinate that's doing all the work here, we get the projection in 1 dimension, and it's given us histograms for each one. So you can see if we project on the first linear discriminant coordinate, we get setosas really clearly separated. Versicolor and virginica are also separated, but there is some small overlap between them. Okay. And we can also just look at what PCA does here. So remember, if we do PCA, we use a PR command, PR comp command on the x's, and we don't tell PCA the labels, the species here, the y. Yeah, so PCA only has these the 4 measurements, the numeric measurements. It doesn't get given a species label. Okay, and if we plot this, we get a plot like this that we've seen before. And you can say, you know, this is doing well. The things are clearly separated, but they're not linearly separated by the coordinates. So the first coordinate no longer cleanly separates versicolor and virginica. I mean, it's clear where we should draw the line, right? But it'd be a diagonal line rather than a vertical line. And there's no reason PCA should separate these populations out, because PCA wasn't designed to do that. PCA is designed to maximize variance in certain directions. Okay, but you can see we can still see the pattern here. It's just not cleanly separated to groups. And in other examples, it'll be even less clean. So finally, I just want to comment on the links between the maximum likelihood discriminant rule we saw before and Fisher's discriminant rule we've just looked at. So in the case where G equals 2, so there's only 2 populations, it turns out that Fisher's rule and the sample M1 rule are equivalent. They find exactly the same partition of space. Now, if we have more than 2 populations, then the methods aren't the same. They'll give different classifications. Now, if you think back to the maximum likelihood rule, we assumed there that those populations were from a normal distribution with the same covariance matrix. And if that assumption is true, then linear, the ML discriminant rule will be optimal in some sense. It'll be the right thing to do. But in many cases, we don't know whether the populations really are normal, and we won't know if they have the same covariance matrix. And so in that case, Fisher's discriminant rule requires less assumptions and might be the better approach. There are also links between linear discriminant analysis and many other methods, particularly linear regression and CCA, canonical correlation analysis. So just to comment on the link between linear discriminant analysis and linear regression, in the case where there's 2 groups, let's suppose we've got a vector y that is it indicates which group we're a member of. So 1 if I is from population 1 and -1 if it's from population 2. We could think about fitting the linear regression model y, which is x beta plus epsilon. And if we do that, it turns out that the beta we find here is the same, essentially up to scaling, as the first eigenvector of W inverse B. So we're getting the same kind of answer out of linear regression as we are from linear discriminant analysis. So if we check out with the iris data, I've coded up an indicator y here that is just either +1 or -1, depending on whether you're species virginica or setosa. And then I've fit the linear model that says predict this vector y using the sepal length and sepal width. And then I've just looked at the ratio of the coefficients. And we get a ratio of -0.88. And if we do LDA as well, and look at the ratio of those coefficients, we find similarly a ratio of -0.88. So they're doing the same thing, they're finding the same direction in the data. So there's all kinds of links between these methods, between the different flavors of discriminant analysis, between CCA, linear regression, and so on. Okay, so they're all closely related.